Hello, guys. It's Tumor Teaches again um, with another little tutorial here, and now we're going to start talking about some more fun stuff. We're going to be talking about relative atomic mass and the mole concept. First, we're going to talk about relative mass. Atoms are quite small, and to actually get the mass of a single individual atom would be very difficult because of how small they are. In fact, uh, yeah, you really can't. So we in order to determine how heavy an atom is, we use something called relative atomic mass, and the standard we use of comparison is a particular isotope of carbon, which is called carbon 12. An isotope is just sort of, um, I suppose, a version of an element. So we use carbon 12, and we just say that that has a mass of exactly 12 atomic mass units, and then from there we can sort of go from there as a standard. We can use that sort of as a baseline to measure the mass of other atoms relative to it. So, for example, the average mass of a chlorine atom is about 35 atomic mass units. So, it's 35 over 12 times heavier than an atom of carbon 12. So, it's about 3 times heavier than your average carbon 12 atom. For oxygen, it's about 1 and 1/3 the mass. Uh, and so on and so forth. You get the idea here. We call that 12 so that when we divide by 12, since carbon has an atomic carbon has 6 neutrons and protons in its nucleus, hydrogen turns out to be a mass of about 1. Um, and then there's that to it. Relative molecular mass is just the mass of a molecule, and the way you determine that is you just take the sum of each atom in the molecule. So you just add up the masses of the you just add up the individual masses that make up the molecule. So, for example, here for carbon tetrachloride, there's one carbon atom, and that has a mass of 12, which you can get off the periodic table. And then there are four chlorine atoms, which each have a mass of 35.45 grams. So the total overall calculation is 12 plus 4 times 35, which gives you that number there. For O2, there are two oxygen atoms, so we just take this mass here and double it, and you get this number here. Um, you could do the same thing for an empirical formula. Um, it's called something different, but it's essentially the same thing. You just call it a relative formula mass. You just take the mass of the empirical formula. That's what it is. So, relative atomic mass based off an element. What's quoted in the periodic table. So, on the periodic table, most good ones anyway, you should have the element number on top, followed by the elemental symbol, and then there should be a mass number pretty much at the bottom of the square. Um, uh, what that number is there, it's actually an average because each isotope has a different mass, a slightly different mass. And when we go into topic two, you'll understand why that is. But for now, you'll just sort of have to take my word for it. So the relative atomic mass of an element is just given as an average. So here, not so for example, the way we calculate the atomic average mass here is just like so. So since 99% of carbon is carbon 12 and 1% is carbon 13. So we just take 98% of 12 and 1% of 13, add them together, and we get 12.01 as the average atomic mass. Uh, I'm not going to go over this mass spectrum stuff because we go over it in topic 11. However, that's sort of how we do it. Now, however, what we will talk about is the mole. The mole, in essence, is people always say it's the chemist dozen, and you know what? They're right because all a mole is 6.022 times 10 to the 23 something. So you could have a mole of atoms, you could have a mole of roses. That would be a lot of roses, and so on and so forth. It's just a number, like akin to a dozen. So, for example, the mass of one particle, one so in 1.01 grams of hydrogen, there are 6.022 times 10 to the 23 molecules of hydrogen. Remember, there's 6.022 times 10 to the 23 atoms of hydrogen in 1 gram of hydrogen, in about a gram of that. So So, however, um, that's sort of an unofficial definition. And that's sort of the one I like to work with in terms of understanding. It's a counting unit like the dozen, and it's really not that difficult. Um, if you think so logically, if you think this out for a moment, H2O, there are two hydrogen there are two hydrogen molecules in every molecule of water. So if you had a mole of them, or 6.022 times 10 to the 23 of them, naturally it only makes sense that there's about 1.2 times 10 to the 24 atoms of hydrogen, because 1.2 times 10 to the 24 is just double that of 6.02 times 10 to the 23. So it's just a counting unit like the dozen, and you can really treat it like that. So if you had a dozen water molecules, there would be 2 dozen hydrogen atoms, or 24 of them, and sort of in a similar vein. My point is that don't be scared of it. You just use it like you would a dozen, and you'll end up fine. However, if you're ever asked to define what it is, the formal definition is the number of carbon 12 atoms and 12 grams of carbon 12. Bit of a mouthful. Just honestly, that's just one of those things you have to memorize, or you really don't. And then molar mass as the mass of 1 mole of any given substance. And the way you calculate molar mass is the same way you did atomic mass, because uh, what's convenient here, the way we did things, is that uh, if you switch the AMU out for grams per mole, we, essentially, yeah, you just do the same thing as you molecular mass, because that number is also the number of grams in 1 mole of it. It just happens to be a nice coincidence. I don't know if there's any real logic behind that, but for example, there is for every 1 gram of that, you have a mole of hydrogen atoms, and so on and so forth. So for example, the relative atomic mass of iron is 55.847 AMU, so therefore the molar mass is 55.847 grams. So, and for every mole of iron, you have every 56 grams or so roughly of iron, you have a mole of atoms. You could use those newfound conversion factors to go from grams to moles to atoms, and so on and so forth. So, for example, let's do a conversion. Let's do one here. So let's do F. Just as an example. I'm not going to go through a lot of them. Again, if you guys want me to post like a separate worksheet, I would be more than glad to do so. But until then, let's do 6.022 times 10 to the 23 atoms to grams of CO2. Well, I happen to know that for every 6.022 times 10 to the 23 atoms, I can write out a string of conversion factors here. Again, so again, I'm writing out the first conversion factor here. So first, I would like to convert this into moles, and I happen to know that there are 6.022 times 10 to the 23 atoms in every mole of, that should say molecules, my bad. That should say molecules, my bad. I know that for every 6.022 times 10 to the 23 molecules of that, there's 1 mole of them. And again, I'm just writing them out in such a way such that my units cancel out here. Okay, just lost track of where my mouse was. So we write that out, cancel that, and then I happen to know conversely. So now we have units of moles here. So 1 mole. My headphones disconnected again, of course. I think it's because there's no audio playing. There's no audio playing through my damn headphones, so that's fine. Um, Whatever. My point was is that here. So now that we have 1 mole, so and I know that a mole of this stuff weighs So carbon is 12. 2 oxygens is 32. That would be 44 grams and 1 mole. So that happens to cancel out, and the answer is 44 grams about. You might get a more accurate number, but I'm too lazy to go out getting the accurate numbers out, and this is just for the sake of example. So, um, combustion analysis. Do I need to go over this? Uh, I'll go over it in a later video when we do topic 11. Yeah. So, thank you very